In 1929, scientists expanded their understanding of the universe with discoveries that eventually led to the realization that all matter, including humans, is made from elements forged in the hearts of stars. By 1957, scientists further unraveled that the sky is more than a spectacle, it's a window into an incredibly dynamic universe that shapes our existence. With so much happening in the cosmos, events sometimes affect us directly, though we might be oblivious to them until their consequences reach us. One of the most fascinating celestial entities currently under scrutiny is Betelgeuse, the iconic red supergiant star in the Orion constellation. Historically among the brightest stars in the night sky, Betelgeuse has recently exhibited unusual behavior that has astronomers intrigued and slightly concerned. This giant star has begun vibrating violently, sparking speculation about its future and its potential to influence our cosmic neighborhood. Betelgeuse is no ordinary star. It is among the largest stars ever observed, with a mass estimated to be about 20 times that of our Sun. While it appears as a reddish dot from Earth, its true nature is far more complex. Situated approximately 640 light-years away from us, this distance may seem vast but is relatively close in cosmic terms. If humans could travel at the speed of light, an unimaginable feat, it would still take over 640 years to reach Betelgeuse. In practical terms, however, it would take more than 12 million years to complete this journey with current technology. This perspective underscores the star's size and power, as well as the monumental distance separating us from it. Despite its appearance, Betelgeuse is anything but serene. Known as a pulsating red supergiant, its brightness varies significantly over time. When the star expands, it appears brighter. When it contracts, it becomes slightly dimmer. These fluctuations occur over long cycles, with brightness changes taking tens to hundreds of days. Astronomers have observed cycles of varying lengths, with the shortest lasting about 185 days and the longest extending over 2,300 days. Sometimes, these changes follow a predictable pattern, a phenomenon known as the V-band magnitude. For instance, in February 2021, Betelgeuse registered one of its lowest V-band magnitudes at around plus 1.61, a notable drop from its typical brightness. The distinctive reddish hue of Betelgeuse is due to its cooler surface temperature, which hovers around 3,500 Kelvin, substantially cooler than the Sun's 5,500 Kelvin. Despite its massive size, Betelgeuse's cooler temperature results in a lower energy output, making it appear dimmer than the Sun. However, recent changes in Betelgeuse's behavior suggest something unusual might be happening. A leading hypothesis is that Betelgeuse's helium shell is undergoing a fusion phase as it progresses through its stellar life cycle. In stars like Betelgeuse, hydrogen fusion typically creates helium in the core. When hydrogen fusion slows, the outer layers expand, marking the red giant phase. The accumulated helium in the outer shell can ignite secondary fusion, producing elements like carbon and oxygen, which release energy and cause the star to expand and contract in visible cycles. These pulsations are often accompanied by mass ejections, with Betelgeuse shedding outer layers through strong stellar winds. This mass loss contributes to its rhythmic pulsations, creating a heartbeat effect that makes the star appear to blink in luminosity. Scientists studying Betelgeuse use various techniques, such as photometry and spectroscopy, to analyze its changes. Photometry measures changes in brightness over time, while spectroscopy studies the star's emitted light across different wavelengths, revealing details about its temperature, chemical composition, and movement. Together, these methods allow astronomers to piece together Betelgeuse's internal processes, understanding how its luminosity fluctuations correspond to deeper physical changes. Astrophysicists also use complex computational models to simulate Betelgeuse's dynamics. These models incorporate equations related to stellar structure and nuclear reactions, providing insights into the star's life cycle and illuminating the mechanisms driving its pulsations. Beyond fusion and mass loss, stellar convection may also influence Betelgeuse's variability. In supergiant stars, energy from the core is transported to the surface through convection, cyclical movements of hot and cool material. These currents emit energy as light, affecting the star's brightness. When convection fluctuates, it can cause periodic changes in brightness, with these pulsations reflecting shifts in energy transport. Some stars exist in binary systems, where two stars orbit each other closely, allowing material transfer from one to another. This exchange alters internal pressures and fusion reactions, often disrupting the star's equilibrium. The forces involved in binary systems can induce expansions and contractions in brightness as stars attempt to stabilize under these gravitational forces. Such mass exchanges can significantly alter a star's evolutionary path, driving changes that wouldn't occur if the star were isolated. Historically, astronomers studied stars as individual entities. Today, advanced technology enables scientists to examine complex interactions, reshaping our understanding of how stars behave in binary or multiple systems. For Betelgeuse, however, there's another possibility that may account for its recent pulsations. It could be nearing the end of its life. Like all massive stars, Betelgeuse maintains a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion in its core. Over time, as its nuclear fuel depletes, this balance shifts, causing the core to contract under gravity. This contraction raises the core's temperature, initiating a final phase of intense fusion that produces heavier elements like carbon and oxygen. This process eventually leads to the formation of an iron core, which is significant because iron fusion absorbs energy rather than releasing it, destabilizing the core and setting the stage for collapse. As gravity overwhelms the core's weakened energy output, Betelgeuse's core could collapse in on itself, triggering a supernova, a stellar explosion of unimaginable magnitude. If this were to happen, Betelgeuse's outer layers would be ejected at incredible speeds, resulting in a burst of light so powerful it would be visible from Earth even during the daytime. The explosion would rival the brightness of an entire galaxy and could last for weeks or months. Though Betelgeuse's distance from Earth would prevent catastrophic consequences, a nearby supernova can still impact our planet in several ways. Gamma-ray bursts, GRBs, high-energy events often associated with supernovae, could potentially damage our ozone layer if Betelgeuse were closer, exposing the planet to harmful ultraviolet radiation that would affect human health, agriculture, and ecosystems. Additionally, the electromagnetic pulse, EMP, from a supernova could disrupt electronics and cause widespread power outages. The energy released by such an explosion might even alter Earth's weather patterns, potentially impacting ecosystems and food security. If, after the supernova, Betelgeuse were to collapse further into a black hole, its gravitational forces could disrupt nearby celestial bodies. Material from the star would fall into the black hole, forming an accretion disk that emits intense radiation, which could harm planetary atmospheres and ecosystems. While the gravitational pull of a black hole located 640 light-years away would not directly affect our solar system, the transformation of Betelgeuse into a black hole would serve as a spectacular reminder of the powerful, sometimes dangerous forces that exist in the universe. The life and potential death of Betelgeuse encapsulate the mysteries of stellar evolution and the immense power of cosmic phenomena. Its fate, whether a supernova spectacle or a silent transformation into a black hole, offers astronomers and humanity alike a rare opportunity to witness the grand finale of a giant star. As our understanding of Betelgeuse and similar stars deepens, so too does our appreciation for the delicate balance and vast forces that govern the universe, reminding us of our place in the cosmos. Betelgeuse's recent fluctuations and potential for a supernova event hold a unique place in the study of stellar evolution, sparking both scientific intrigue and widespread fascination. The ongoing changes in Betelgeuse's luminosity and size are a visual reminder of the dynamic processes occurring within massive stars, providing astronomers with a real-time example of the stages that ultimately lead a star to either supernova or black hole formation. Betelgeuse's fate also underscores the role that massive stars play in seeding the universe with heavier elements through their life cycles and explosive ends. When a supernova occurs, it doesn't just create a stunning visual spectacle, it disperses newly forged elements like carbon, oxygen, and iron into surrounding space. These elements eventually become part of new stars, planets, and even living organisms, contributing to the cosmic recycling that is foundational to galaxies. In a sense, the supernova process is responsible for the very building blocks of planets, atmospheres, and life as we know it. Should Betelgeuse explode within the coming decades, the massive outburst of stellar material